We're going to spend a lot of time talking about harmonic waves, and the reason is we can write any periodic wave as a sum of harmonic waves. This is essentially a Fourier series, and so any periodic function can be written as a sum, in some cases an infinite sum, of sines and cosines. So here is how we're going to go ahead and define this. A right here is the amplitude of the wave, and we have a wave of wavelength lambda and period t. And so the reason we have 2 pi x over lambda, well, essentially what lambda is saying is that's how often this thing has to repeat. So when we're talking about sines and cosines, the sines and cosines repeat themselves after having gone through 2 pi radians. So after x has increased by some integer number of lambda, we're going to end up with a integer of 2 pi, which is simply just one cycle. Same thing with the time factor. The period is defined as the time it takes for the wave to repeat itself, and since it's 2 pi radians to repeat a sine or cosine, then anytime t, little t, the time, over the period is an integer, then we're going to get a repeat in our cycle. So we can think of the wavelength essentially as the repeat distance and the period as the repeat time. And so the wavelength then is defined as the distance between any two similar points on the wave. We can choose any points. We can choose the trough. We could choose the distance between two peaks. We could choose the distance between these two 0 points. It's always going to be the same distance. Now, in terms of time, what I've done is I've sketched the wave here at 3 different times. At time t, t plus half a period, and then t plus a full period. And so you'll notice that after half a period, well, the peaks and valleys have essentially switched places, and then after a full period, we're right back where everything has lined up again. In fact, nothing looks different than it did before. So that capital T then is the period, the repeat time it takes for the wave to look the same again. A couple of things we need to define. The spatial frequency, k, is defined as 2 pi over lambda, and that's essentially coming from the fact that we're going to go ahead and in our equation, we're going to combine 2 pi and lambda right here. We're also going to do the same thing with 2 pi and t there. So our spatial frequency k is 2 pi over lambda. Our angular frequency omega is 2 pi over the period. So with these definitions, then we can go ahead and rewrite our wave like this. Now, one thing we should just double check is that we're still going to satisfy the wave equation. So one thing to keep in mind is that the velocity of the wave is actually omega over k. And so with that, we can take and rewrite our function by factoring out a k from both of these terms as k times x plus or minus vt. In other words, we still have a wave. We still have something that's going to satisfy the wave equation because the argument is still x plus or minus vt. A couple other things, the phase of the wave. Since we're dealing with sines and cosines, one way to sketch these things out is in terms of an angle. And we know that how this thing looks, in other words, this would be pi, this would be 2 pi, this would be pi over 2, and so on. And so what we do is we take a look at our spatial wave, and we then just line it up, and we say, well, this point right here corresponds to the peak here, which corresponds to an angle of pi over 2. This point on the wave corresponds to pi. This point here would correspond to 2 pi, and so on. And so when we talk about the phase of the wave, essentially what we're doing is we're relating the location on the wave itself to an angle. Now these angles don't have, they're not angles in a physical sense, but these still are a relationship due to the nature of the sine and the cosine. So essentially then the phase, phi, is given by our argument. In other words, phi is just kx plus or minus omega t. One other thing, we may not have a wave function that actually starts right at the 0 or right at 1, and so we need to be able to shift our wave function around. And so we talk about the phase shift. So we have here a wave that doesn't start at one of the sine or cosine points, and so we need to figure out how this thing needs to be shifted. It turns out that the shift in the phase is just the inverse sine of the starting value divided by the max value, or the amplitude of the wave. So this right here then allows us to write any sinusoidal function that we possibly want, shifted as far as we want. One thing to note is that since sine of theta plus pi over 2 is cosine, that if our phase shift is pi over 2, we can rewrite our sine function as a cosine function, and vice versa.